सर नागार्जुन रेड्डी गारू सर is it audible?
Hello, good morning, sir. Am I audible?
Yes, sir. It is audible, sir.
Okay. Sorry for the delays because of the connection issues.
Oh, okay, sir.
Am I not visible, right?
Yeah, you are not visible. Yeah, great. Yeah, it is visible now.
Okay.
Just as per formality, we will start that. So then you can proceed. Okay, sir?
Yep. Okay, sir. Sure.
Yeah. Very good afternoon. This is the last day as well as the last session. Today, our speaker, Mr. Nagarjuna Reddy, Senior Engineer, E-Mobility Division, ZF Group, Germany. The topic is E-Mobility, Insight to Electrification of Automobiles. Now, our chief guest introduction by Bhavana ma'am. Ma'am, you can proceed.
Thank you, sir. I take this pleasure to invite our today's resource person, Nagarjuna Reddy, sir. So he did his Bachelor's in Electrical and Electronics Engineering from JNTU Kakinada, and master's degree specialized in power electronics. Started a job at Robert Bosch Engineering and Business Solutions Private Limited. Has been working in electrical power train development and test bench engineering area for more than 8 years. Currently employed as specialist in test bench engineering and automation at ZF Group, e-mobility division in Germany. Has a technical expertise varied through HIL system design, development simulation, providing various test solutions, installation, testing, support, and maintenance, SW development, requirements, analysis, etc. in e-mobility. As an individual interested in continuous personal and professional development and willing to help students or professionals whenever need support and guidance. Thank you for giving me this opportunity to introduce our today's resource person, Nagarjun Reddy, sir. Sir, I request you to continue the session to our participants.
Thank you very much for the nice introduction. Yeah, sorry for a little delay for a few minutes because of the connection issues. So as said, my name is Nagarjuna. I'm currently working in ZF and from Germany. And I don't know the audience exactly whom I'm trying to discuss with. Is it students or lecturers, sir? Can I know?
Faculty, sir.
It's a part of faculties, research scholars.
Okay, great. Yeah, I only have thought about basic introduction of e-mobility. I'm not sure how much deep everyone is into this topic. So I was thinking to have only a basic introduction and basic overview into the e-mobility topic. So I might be looking at my bigger screen to explain you in a presentation, but maybe I'm a little bit off from my camera because I also logged into mobile because of connection issues. So please don't mind. And if you have any doubt in between, or if you have any critic point in between, please raise it and please ask. And also, of course, I will try to have some minutes at the end to have some queries if you have. And yeah, we can continue. So I will try to share my screen.
Yes, sir, please.
Yeah. Is it visible?
Yes, sir, visible, sir.
Great. Okay, thanks for the feedback. So the topic, as I discussed with Mr. Muthu sir, that e-mobility and insight into electrification of automobiles. And the electrification of automobiles has been there from many years. And I also tried to keep this presentation as simple as possible with the open source links so that everybody can access to it after the presentation. And I will be forwarding this document as well after the meeting. So it is not necessary to note it or write something down. And it is also, as I said, simplified topic that I'm taking today. And the advanced topics may be deeper inside each component or something relevant more towards some technical aspects. We can also have a plan of that later. Yeah. So here, as we see, the e-mobility definition itself is simply put into electromobility, so which represents the concept of using electric powertrain technologies, in-vehicle information and communication technologies, connected infrastructures to enable the electric propulsion of vehicles. So either it could be e-bus or e-bikes and normal cars. Bikes are bicycles basically, and motorbikes, of course, the motor-based bikes. And everything which has been from past many years are running with diesel, gasoline power sources, and it has been into the electrification of these vehicles to reduce the pollution, to reduce the CO2 emissions, and also to reduce a lot of other aspects where the fossil fuels are saved, and also to make more greener energies into the into application as much as possible. And so the electrification itself is to remove the traditional source of energies like diesel and gasoline and to replace them with the electric propulsion systems. And that has been the basic definition. And why do we need e-mobility? So as everybody, I think, know already, why are we moving slowly towards electric vehicles and electric mobility? So today there are like almost 1 billion motor vehicles. This is a statistic, I think, from back like 2 or 3 years ago. So it would be much more now. So more than 1 billion motor vehicles, where most of them are car, like 70% of them are cars, normal passenger cars. And according to the current projections, this number is expected to double in the next 8 years now. So until 2030, it will be doubled. So that's the acceleration that is taking place in terms of increased number of vehicles in the world and increased number of vehicles for the transportation possibilities in the world. So until now, car has been the almost entirely dependent on imported, rare, increasingly more expensive fossil fuels. As we know, the oils are pertaining to only particular locations in the geography. So into the Arab countries or Russia, or into some of the countries where the oil reserves are really available. Not every country has that. So they have to import it, and these are also limited. So this implies the challenge of reducing the traffic-related CO2 emissions and pollutions and the dependence on oil imports. So these are the three main reasons if you see. So the pollution levels, the CO2 emissions, and the dependency on oil imports and exports is what is targeted to reduce because of the electrification concept. So this is why advancing electric mobility is a focus of the government's policies of many countries. And it is also trying to improve the quality of life in our cities because of the reduced CO2 and pollutions, and also the competitiveness of the automotive industry. So at the moment, the automotive industry is also most of the companies, and I would say almost every company is trying to put their efforts, putting their resources into place to develop electrified automobiles. So this is basically the pillars of economy of any country which is having its economy based on electric automobiles. Yeah, but to really exploit the huge potential of the electric propulsion to actually reduce CO2 emissions, it needs to also combine with renewable resources. So this is where it comes with actual advantage. So not only to reduce CO2 emissions by just using batteries, if you also combine this with the renewable sources by charging the batteries or charging the energy sources that are really required for the automobiles by using renewable energy like PV, photovoltaic cells, or wind energy, or any other renewable energy source to just charge these batteries or charge the source that is required. And this will, as a combination, really give a lot of advantage in reducing the pollution and also making more green of energy. Yeah. So otherwise, we simply move the emissions from the car to the power plants. So if you don't have this renewable energy source in combination to work for us, of course, charging the batteries or having chemical process of fuel cells, everything requires energy. And this energy as a source, we only have power plants which are running either on coal or hydraulic or maybe atomic energy sources and so on. So basically, if we cannot inculcate the renewable energy sources, it is indirectly putting again more burden on the power plants, and this is not really reducing the CO2 emissions, but just diverting to some other source. Yeah, so by linking these two industries, we are linking two industries where I just referred to Germany because Germany is one of the pioneer in automobile industry, and they also have a lot of strategies at the moment working out to increase more electric vehicles into the market, and also to see on the other side use more renewable energy sources as well. So systematically linking these two with the intelligent charging techniques and feeding the electricity from wind and solar into the grid gives the Germany or any other country for that matter a significant advantage. So with the help of electric cars that charge at flexible times, it becomes easier to so integrate into the system and also share of a fluctuating generating power. So if you have more power sources and also it's fluctuating power, if you have more or less load on the other side, and if you have electric vehicles which are getting charged from these power supplies, then it also reduces this fidelity of having fluctuated powers and fluctuated currents. Yeah. So this is advantage of also integrating into the grid systems. Yeah, this is the basic introduction of e-mobility. I hope it's clear. Yeah, then we see a little bit of history of electric vehicles from where it started, how it actually evolved for these years. And also, so these are the topics which I would cover in the next coming few minutes or an hour or so. So what are electric hybrid vehicles and their history and the major components of the electric vehicle, like exactly which components are available, what is the function of it, and how each one is really be working inside the vehicle to make it as a complete electric vehicle. And also we see a little bit of the 4-quadrant operation of electric motor or electric vehicle, how the torque and speed really makes it to work in all the 4 quadrants. And also the regenerative braking, which is one of the most advantage and most advanced feature of electric car, where it saves a lot of energy and also gives an advantage of increasing the efficiency of the system. So we see a little bit of a short video of 2 minutes to make it really understandable to everyone. And the efficiency of EVs, like how much percentage exactly they really give when it is in operation with battery, inverter, and machine together. And then slightly I go towards touching the industry, like in the industry, how the development process goes on. So a best example of the development engineering process is the V cycle. So there are many models available, but I'll try to give short introduction on the V model, which is very popular in automotive development. And the testing procedures of core components. So how do we test these components after the development? So my area of work is also building the test systems and more into the testing area. So I thought it would be better to give a little bit of insight into what I know. So other areas, I know a little bit of overview, but I'm not too deep into them. So I try to give the perspective of testing procedures and how the testing could be done in different stages. So hill, sill, mill, and so on. It's also a very brief introduction on how the test automation is done. So it is also my expertise area, but I don't go too deep into that as well. So just introduction and also some basic e-mobility concepts that we are working at ZF. Okay, so let's move to the brief history. So I gave the open source links here. I didn't prepare anything on my own or anything from my company. So these are open source, so everybody can refer to it later. Okay. So this is prepared by, I think, one of the IIT student from 2011, but it doesn't matter. It has some introduction of the history of electric vehicles and electric components. So I took it for basic presentation and information. So here we can see the basic background of electric vehicles, when it really started. If you really look at the history of the electric vehicles development, it really started in 1904, which is way back, like more than 120 years or close to 120 years now. So such historic progress we have seen in the last many years. And it has started by Siemens as a basic electric car, which also funny to see how the electric or car itself looks like back then. And slowly it started like Thomas Edison by working with Detroit Electrics. They also have developed between this period a lot of electric vehicle technology. And for example, yeah, travel horn, how it also looked like between 1902 and 1919. In 1961, how Henry kilowatt electric car looks like. So how is it from General Motors? How is it from City Car, from Vanguard company? So these are some of the pictures that shows how they started with electric cars and also the development of it. And Chevrolet, they also have started in 2017 to electrify the vehicles. And Tesla, as we know, it's very popular in developing the electric vehicles. So it has the only car model available, and it is only electric vehicle. They're not selling any other. So this brand is meant for electric vehicles, as we already know. And yeah, that's the short history of electric vehicles. And here we see how they work in principle. So very basic working principles of electric vehicle. So any electric vehicle, it contains few major components, like you see in the bottom. So PPT is not really that sophisticated, but it really shows up what are the components that are available on an overview level. So we have basically a battery. So that's called traction battery. So traction battery is the high voltage battery. So the terminology to just exemplify, So anything that is more than 60 volts is called high voltage battery. So for most of the hybrid electric cars, we use a battery which is more than 60 volts. And there are some hybrid vehicles which also use 48 volts, which is also considered to be a traction battery. So this is just another example. But most of the times, if it is mild electric or maybe plug-in electric vehicle or a pure electric vehicle, the battery level is more than 150, 200, 250, 300. Now it's been up to 600 and 800 volts of battery as well in the very modern concepts. So that's the range of traction battery level. So starting from 60 volts, it can be up to 800 volts. Yeah, and we have basically the controller. So the controller is a motor controller. So as we know, we need energy for the wheels, and the energy for wheels to drive a car requires a motor, and this is the motor. So I'm coming from a little bit on the reverse side now. So these are the wheels, and wheels should be driven by a motor, and motor should be controlled by a controller. And if this motor is AC, and if the traction batteries are DC, as we know, and we need a converter, which is nothing but an inverter. So inverter is a DC to AC converter. So it converts the DC energy from traction batteries to AC energy to drive the motor. And this is done by a motor controller, which is nothing but an inverter. And this is a major controller in the complete electric vehicle, where it is the master. It is trying to control everything with respect to torque speed and its efficiency algorithms, IDIQ control. Whatever the control we take, the controller has a microcontroller or a DSP, and this is flashed with a program which contains all the algorithms and control techniques that is required to control the motor. And it has a lot of sensors and feedback signals coming up, and based on which it is trying to control the complete electric car by controlling the motor. Yeah, that's to put it in a simple way. So this is the line which you see: battery, motor controller, an inverter, and a motor or a machine, which can also be used for generator. We will see that later. So these are the three major components we see in every car to really drive the vehicle. And this is called traction drive system, these three components. And apart from that, we also have some auxiliary components, which are also required to keep all these three in operation. For example, we see charger. So we need charger, for example, if it is a plug-in electric vehicle, or if it is a pure electric vehicle, we need a charger to charge the traction batteries. So from the external an AC energy source, it has to just charge the DC batteries. So you can already expect that this should be an AC to DC converter with proper regulation concepts. Yeah, that's about charger. And we also have DC to DC. This is required because in any car, either it is a diesel or gasoline or electric car, it doesn't matter. The auxiliary batteries, which is of 12 volts, is always there. And this auxiliary battery is for providing power supply to low voltage components like lights or internal radio system or internal ECUs. So ECU is an electronic control unit. So each control function in a car requires an ECU, electronic control unit. And in an average, let's say BMW car, we have like 60 to 70 ECUs, electronic control units, right from small units to bigger units. So it varies across different functions. And for all those ECUs and controllers, we need an auxiliary battery, apart from traction battery, because traction battery is high voltage and all the low voltage components, including these ECUs, working on only 12 volts. So we need a 12 volts battery, and this has been there in the diesel gasoline cars and vehicles as well. And electric are also having that fixed in the electric vehicle. So there is no change in it. But if we want to use the auxiliary battery without any power issues, we also need to charge them. In the normal conventional vehicles, this electric battery of 12 volts, so even 24 volts in commercial vehicles. Commercial vehicles are like trucks, lorries, or buses. So the bigger vehicles, the commercial vehicles, require sometimes the auxiliary battery of 24 volts. So either it is 12 volts or 24 volts, this requires to be charged. In the normal conventional vehicles, it uses the energy from engine, and there should be internal conversion drive, which is trying to take the mechanical energy from the engine and trying to convert it into electric, and this electrical energy will be converted again back to the battery DC source, and that is trying to charge the auxiliary battery. In a pure electric vehicle or plug-in electric vehicle, it makes more so most of the electrical engineering, we know it is a DC-DC converter. So DC at the input, which is a high level, and DC at the output, which is going to the auxiliary battery. And DC-DC controller can be any type of controller depending on several suppliers, several manufacturers, several OEMs. OEM means original equipment manufacturer. So any major car supplier or manufacturer can use different type of strategies to, or algorithms developed to flash and set the controller of a DC-DC so that it can have effective use of charging systems. Yeah, this is another major component. We discussed DC-DC, and we have several internal contactors, protectors, and so on. And differential is basically to transfer the mechanical energy from out of the motor to the wheels. It goes through the gearbox in between. So even if it is an electric vehicle, we have a standard gearbox. So standard ratio like 10:1 or 9:1, something like that we use. Yeah. Can somebody mute? Okay, thank you. So these are the basic components of an electric vehicle. So wherever you see, these are most common, and the functionality is also most common. And what differs is the internal control systems. So the controllers, if you see here, we have only motor controller, DC-DC controller, and the charger also have some controller to have effective charging. So these three controllers have different algorithms to have different ways of controlling and different ways of managing the systems, their own systems. Yeah. And there are some informations on which kind of motors and which kind of voltage levels it has been used, but I don't go into it. You can also refer to it later from the presentation and link. And these are some of the examples how the motors look like in the very beginning days. So forklift motor, AC motor, so three-phase, how they have been used. And some example of how a DC-DC is working. So with a DC here and DC motor. So we don't use. Can you please mute? Hello. Yeah. Okay. Thank you. So we have several types of motors, as we basically see like DC motors and AC motors. And there are several advantages of AC motors, of course, because of its effective power efficiency and also simple design and simple controlling possibilities. We go for AC motors, and we use also three-phase AC motors. It's much more effective, much more powerful and power possible. So we don't really see it the DC motors, and we always use AC motors. And you see here the same thing again, as we discussed, with several components put in together. So a traction battery, which is of 300 volts, here is an example, and a controller to control the DC, to control the AC motor, so that the AC motor can give output of mechanical energy, which can be going to transmission, which is also including the drivetrain and wheels of the electric vehicle, a normal car. And a charger here to really charge the 300 volts battery. And the controller also includes a DC-DC controller in general to also power up the 12 volts battery. Yeah. And here is a simplified view of how a AC controller looks like. AC controller is what he means here is a DC to AC converter. So as we already have seen, we have been using on most of the cars 3-phase AC motors, and the 3-phase AC motors require an inverter which can convert the DC energy into an AC one, and for which we need silicon based switches, and it can be MOSFETs, it can be IGBTs, it can be SiCs, silicon carbides, which is the latest technology. Here we can see an example with an IGBT, so integrated gate bipolar junction transistor. So these IGBTs, if it is a 3-phase, we need to use at least 6. You can see here S1 to S6. So these are 6 IGBTs which are placed in a way to transfer the DC to AC. So I may not go deep into how the AC inverter works. So DC to AC inverter works. It is simple conversion of DC into AC with specific switching cycles. So we have a controller, and you can see here for each IGBT, a gate here, and which is a major source to turn it on or off. So a gate pulse is used from an controller. So this controller output can be given to this IGBTs so that it can be switched on and off with particular logic to transfer the energy from DC to AC. And there could be several types of such control aspects. It could be simple inverter, it could be multiple multi-level inverters. It could also be different type of algorithms to switch in a specific way. Yeah, there has been several patents, several algorithms designed to really and effectively switch this inverter so that the efficiency of the complete system would be improved. So this has that great of influence to control these switches. Yeah, so this is a simple inverter, how it looks like. And also some information on batteries and charges here. Like we have several types of batteries: lead acid, nickel zinc, lithium ion, lithium polymer, and most of the vehicles at the moment are using lithium ion or lithium polymer because of their possibility of energy efficiency. So in a small compact unit, they can have more energy stored so that it can give longer ranges for the vehicles. So the more energy you have in the battery, ampere hours, and the more distance you can travel with the energy that you have. It's really the proportionate. So the proportional to what distance can is also given by the energy source storage possibility. So that's the reason why, if you see here already, so lithium ion, lithium polymer has the possibility to really store a lot of energy in a small space. So the density of power and the compactness of power storage possibility is higher here. So this at the end is also high energy efficient, and performance is also very good with these kind of batteries. So here it looks like it's a very old image, but the newer cars, if you go inside Google and type how the chargers look like for different cars, you can always see here. So this is a charging port for a vehicle example here, and you have to just plug in like here from the wall socket, which is in our Indian electric single phase 230 volts. We can just give and input it to the charging socket here. And then internally it has a controller which monitors the fluctuations of input AC and then controls to convert into the DC at the output of this controller, and it can charge them to the high voltage battery. Yeah, these are very basic diagram, basic pictures of chargers, but the real pictures looks a little bit different. They're very big at the moment in the current technologies to support really high range of voltage and also high range of ampere hour and higher range of mileage. So it can really go far. So simple charger principle. So charger is basically AC to DC because it has to just charge from AC outlet from a wall socket, which is a house supply, to convert to DC so that it can charge the batteries. So it is basically rectification principle, and this is a simple diagram, but it looks a little bit different if you see AC to DC controllers, which are really used in cars. They have really other sophisticated elements as well. So one example is given here, like Magna charge system, how this is really placed onto the wall, how this is being built and so on. Small example here. And with the batteries, it always comes to certain problems, which also has to be solved by using some algorithms. And that's why you can always think about when it is a AC to DC converter and also charging the batteries, it always has to check several factors. So few of the most important factors are, one of them is equalizing. And a battery is not built with one single cell. It is very complicated to build chemically such a big battery. So what many companies does is they build modular batteries. So modular batteries means we have several small compact cells put in together in series parallel combination to achieve the required voltage range, required ampere hour range. Yeah, even if you see any toy, any small equipments that you have battery powered in your house, it doesn't really work with one single battery. If it is a really high voltage and high current requirement, you have multiple parallel cells. You have to just install them, and based on the voltage and current requirements, then it can be circuited with series parallel combination. Then it achieves the required power level. Yeah, and for which, if you have to charge each equal cell inside the battery pack, then you have to monitor how these voltage levels are. So one battery cell could be of lower voltage, one battery cell could be higher voltage, and we have to always monitor it doesn't go beyond certain limit, like maybe an error or tolerance limit of, let's say, 2-3 volts, if it is a higher battery cell. If it goes beyond these limits, then it may overcharge one cell, undercharge one cell, and at the end, when you see the life cycle of the complete battery, it might give possibility of failing one of the cells or few of the cells. So if it has unequal and imbalanced charging, discharging, cell balancing and equalizing, then over a period of life cycle, you might see failure of few cells, and it is also giving troubles to change the battery cells or complete battery pack for that matter at the end of its life cycle. So it matters a lot to increase the life cycle of the complete battery pack, which is the most expensive one in the car. So that's the reason why you see why electric and hybrid vehicles are really expensive, because one of the most expensive part in the electric vehicle is the battery. So battery production is not easy, and it is also very costly matter. Yeah, that's why we need to take care of the battery as much as possible, and to reduce the effects of such equalizing as much as possible. So the equalizing is, it is trying to make sure all cells are balanced and equally charged and not overcharged or undercharged. Yeah. So example of that here. Yeah, then we have regenerative braking, which is the advantage of the electric cars itself. So they really try to use the energy available when the kinetic energy is available. We will see about it maybe later in our presentation in much better way with a video. It basically trying to make sure during the acceleration phase, the energy flow is like this: battery, inverter, motor. So battery to inverter, inverter to motor. So this is the acceleration energy flow. During the braking, which means you want to brake, and which means you don't want to drive the car with your energy, and you just want to stop the vehicle or brake the vehicle or reduce the motion of the vehicle, which means you're not trying to pull the energy from batteries. You have already the energy available at the wheels, and these kinetic energy at the wheels can be utilized to transform to electrical energy. So the same motor, whatever we have discussed till now, this motor is actually electric machine. It cannot be called exactly as a motor, but for simplicity, I have been just calling it as motor, so that we always think about the principle of using the motor to drive the vehicles. But on the other side, the advantage of it has a regenerative braking. So during the braking process, this electric machine can also be used as a generator. So it acts as a generator by taking the kinetic energy available on the wheels and transform this kinetic energy into an electric energy, which is electric 3-phase AC. And this 3-phase electric AC can be used to again convert to DC and then charge the batteries which are available. So these DC traction batteries can be charged basically when the car is having free energy in it. So the free energy can come either when you're braking or if you're going down slope where the car doesn't really require any energy from the source. So this is the braking and the regenerative braking as a principle used during braking process. And because of which we are trying to use the energy available at the wheels, the free energy to charge the batteries, so that the batteries doesn't really requires charging from external source for this part. If it is a hybrid, it charges from engine. If it is a plug-in hybrid, it has to be charged from socket. If it is an electric vehicle, later it has to be charged from actual house supply. So during the braking process, some percentage of the energy is saved and it is trying to charge back into the batteries, so that this energy we can use again for acceleration process. So this percentage varies several times during the drive period. So during the drive period, we tend to brake, accelerate. Sometimes you go down slope, you go up in the hill. So we have several situations and road profiles where you have these two coming in place. So that means you have many times during your drive, there is a possibility to store the energy and use it again for the acceleration. And this way, we are not wasting the energy like in conventional vehicles. In the conventional vehicles, the braking is the most energy ineffective way of doing it, because it has to just discharge or give out all the energy onto the brake pedals or in the form of heat. So basically, if you have to brake in the normal diesel gasoline vehicles, you have to just brake it and it has to dissipate all the energy in the form of heat or friction when the brakes are really touching the drums. So this is just a waste of energy and we are not really using it back. But in the electric vehicles, or when there is electric vehicle components available, then it is possible to restore this energy for some percentage and you can again use it for acceleration. And this restoration possibility also depends on how big is your battery and which type of vehicle it is. So if it is a very mild type of hybrid vehicle, then it can charge only a little percentage of it during braking. If it is plug-in hybrid or electric vehicle, then it has more widened possibility of taking in the energy available on the wheels, and it can again be later used to accelerate. So these are the factors that is influencing how good is the energy that is being utilized during braking process. We'll come to it also later in our presentation. Yeah, so on the auxiliary batteries, as I said, auxiliary batteries is nothing but 12 volts or 24 volts. Here it is written as 14 volts, doesn't matter. So between 12 and 14, if it is a commercial vehicle, we use 24 volts as we discussed. And if it is a normal car, then we use 12 volts. And this is being used to power up accessories like headlights, radios, fans, computers, or nothing but ECUs, airbags, wipers, power windows, etc., etc. There are many low voltage components available inside an electric car which can be powered using this 12 volts battery. And of course, this is also used to control, used for the motor controller, logic and power electronics. That means the logic controller is the ECU, electronic control unit. Yeah, and for which we need a DC to DC converter. We already have seen that. So an example how a board looks like is just given here. So typical converters are buck boost sometimes can also be used. Yeah, some examples of vehicles like Tesla here, the Roadster model. What is the features? What are the brief features of it? The acceleration possibility to go from 0 to 60 miles per hour in just 3.7 seconds, which is quite fast. In the normal diesel gasoline vehicles, we need more time to come out of the inertia of engine to go to this level of speed. So it takes a few more seconds more for the normal engine controlled vehicle. So comparatively, the battery powered or electric vehicle has a high speed acceleration possibility. Yeah, and its dimensions, just an example. It's really just, these are just the features, so not really important for the technical aspects at the moment. So some, you can also see a battery life. How much is the battery life that can be expected? Yeah, and so what are the locations of all these components inside a car is also exemplified here. You have a battery pack, so which is you can see always on the bottom of the chassis. So this is the of the car, and bottom of the chassis you can see battery pack. So energy storage system, ESS means, I think, yeah. And you have then an inverter, which is the power electronic module, which is here. And output of power electronic module is connected to a motor or a machine, electric machine. And then the output of it is connected to the transmission system. And from the transmission system, it goes to the wheels. And in addition, we have air conditioning systems, computer, navigation, and all many accessories which are also required in the vehicle. So our battery pack look like, so just an example here, but most important thing to know is it is not one battery, it is a combination of battery cells. So we can combine them in series parallel to achieve, let's say if it is 375 volts, and we have to use small cells to achieve this in series to achieve the voltage, and to achieve the milliampere hour or ampere hour, we need to keep them in, to keep them in parallel to achieve the milliampere hour rating of the complete battery pack.
Sir, one small doubt, sir. I think some people,
Sure.
they are chatting in the chat box. Some queries are came, sir.
Okay. Oh, I didn't see that. Okay, sure.
Yeah, in the chat box, like, can you see the chat box, sir?
At the moment,
Or shall I
can check on my mobile. Yeah, I'm able to see my mobile. Just a minute.
Yeah.
I'll keep the presentation here active. Okay. Battery array size, series parallel combination. Okay. What are parameters to okay. Okay. I'm not sure if I can justify 100% about batteries, but I'll try to answer. Let's say, for example, the first question or information is the series parallel combination of battery array size. So let's say, for example, if we have, I'll take some paint. So let's say our battery is expected to have, let's say, 200 volts and 100 ampere hour. Yeah. Okay, and we take, let's say, for example, small cells, 1, 2, 3, 1, 2, 3, 1, 2, 3, or let's say until here we have series parallel and have many battery cells here, and the output is like these are connected again in parallel. I'm not really drawing the best way possible, but I hope it's clear. Yeah, so let's say I'm depicting this as one cell. Let's say each cell is 2 volts and 1 ampere. Just an example, I'm not sure if this cell is really available. Let's say if it is 2 volts, to achieve the voltage in one leg, let's say these are legs, leg 1, leg 2, leg 3. In one leg, we need to have at least 100 cells. So 100 cells into 2 volts is giving 200 volts. Yeah. And similarly, if you want to achieve 100 ampere hour, let's say my one cell is 1 ampere. And to make it 100 ampere, we need 100 legs, because in the series, the current is same. So we need to have 1, 2, and so on. We need to have 100 legs. If you have 100 legs in the parallel, which are connected in parallel, so in the parallel circuit, you know, the current will be added up. So 1 ampere, 2 ampere, and so on, 100 ampere. So if you want to achieve the voltage range, it is a series combination of cells. And if you want to achieve the current range, you need to make it in series in each leg, in parallel. So in each leg to support this 200 volts and 1 ampere, so that at the end of an output of the circuit, you always can get 200 volts, 100 ampere hour. Which means per hour, for 1 hour, if you are really using it for 100 amperes.
Sir?
Hello? Yeah, audible?
Sir, actually, you are saying about the series parallel combination based upon the voltage and current rating of the battery. My question is, suppose we are arranging various batteries in terms of the capacities, that is the voltage and current rating. My question is, if any one of a particular cell or a particular battery is to be as, or all the batteries are to be uniformly charging and discharging in the same category. Suppose if any one battery life is to be somewhat degrade while compared to other batteries, very near to the neighbor battery or very near to the next cell, next array, the battery degradation should be as uniform or differ, sir?
It is different. So the battery degradation also depends on each cell's characteristics. So it's a good question. Actually, if you really think about each cell as a battery, so each cell is a different chemical composition. Even though it is meant for, let's say, 2 volts, 1 ampere is what I said, one cell as an example. So during the life cycle, this battery can come, let's say for 10, this cell can come for maybe 10 years, just for this, for example. And the other cell can come only for 9.5 years. And this other cell can come only maybe 9.7 or something. So each cell has its own special pack of chemical composition, even though they are meant for the same rating and also meant for the same effect on same purpose at the end. Each one is little bit different, slightly different. And the chemical composition that is having between anode and cathode in between the cell, they also have certain characteristics. So that's the reason why at the end of this 10 years or 9 years of period, because of its internal chemical stable composition, it is trying to give whether it can give longer viability to us or it can burst off maybe a little bit earlier. So it is different to each cell, and the same thing goes to different to each leg as well. If there is problem, so the equalization is trying to make sure each cell and each leg is having balanced voltage, balanced currents, so that at the end, everything works as a pack together until the end without giving any problems. But it can happen that, let's say, even I have seen this in the real life as well. One of my colleague, he was using hybrid vehicle, and there were 2 cells out of this combination which has gone bad, which means after 13 or 14 years of use, the battery cells, only 2 cells have were damaged. All the other cells were still working. Only 2 cells got damaged, and the showroom persons, the mechanical or the electrical engineers which are in the showroom, they have replaced these 2 cells internally, and it worked again. And there is also app now with the technology that we can see how the cell balancing is done, how each cell is being used. So if it is a 2 volts, let's say, for example, it is normally capable of between, let's say, 2.5 as a upper level and maybe 1.5 as a lower level. So it cannot overcharge than this, it cannot undercharge than this. And this will imply at the end on its life cycle. If you are trying to make a very good cell balancing technology by making sure you are having each cell and leg taken care to not to overcharge, not to undercharge, these properties are lasting for a long time. But for some reason, because of spikes or because of improper design of internal electric components or also improper design of algorithms, if it is overshooting, let's say, to 2.7 very often, and this cell is prone to get damaged very fast. But this doesn't influence, so let's say this battery cell alone has a problem and all other batteries are healthy, then these healthy batteries doesn't get influenced by it. Understood?
Okay, thank you, sir. Thank you, sir. Okay, sir.
Yeah, so the cell balancing is a little bit of different concept. So maybe we need to really go in deep to see about it. But if you see the general battery characteristics, it has some upper level and lower level for overcharging and undercharging. And if the cell balancing technology is really good, then the life cycle and lifetime of this complete battery pack would be better. And if there are more cells damaged in one leg, for example, then of course it is trying to take more energy from the other packs to really give the required energy. Maybe there is a controller saying that, okay, I have one complete leg damaged or a few of the cells damaged, because of which I have to stop the complete leg so that the vehicle should be in operation. Then it also indicates that it cannot give that much energy as expected. Maybe instead of giving 100 kilometers range, it may give only 80 kilometers, stating that, okay, one leg is damaged. So the vehicle driver can drive up to 80 kilometers, and later he has to go to showroom or he has to go to the repair center and make it repaired or replace the complete battery pack or cell of it. It is possible. But there is a slight influence on the others in terms of operation to extract more energy or to feed the energy back to these cells. But each cell has its own property, and it is not directly influencing on any other cell or any other leg. Yeah, I hope it's clear to a certain extent. If it is not, you can let me know. Yeah. So that's about series parallel combination question. And charging stations, I am not sure how good are in India, but I'm sure definitely charging stations are there in India, but very, very minimal and can be counted on fingers, I think. So I'm not sure. I'm not really following the news as well, how it is in India. Maybe we can Google it up and see how many charging stations are in India. But of course, it has to increase in the coming days if the electric vehicle market has to really go into people and into the passenger car system. Yeah, it has to increase. And I know it's also very slow because not easy to accept the high price electric vehicles on the road, and not many are really coming forward to buy it. As we know how the market goes in India. That's the reason why I think it might be slow in establishing this infrastructure of charging stations, which is also one of the major blocking points across the world. In any country we take, the infrastructure to keep more charging stations, and also the time that is taken for charging, like quick charging, fast charging, many are coming up, but still it is not meeting the satisfaction of the consumer. So if I have to fill the diesel or gasoline, it might take just 5 minutes of time to fill in any of the in-between stations and drive ahead. But if it is to charge only an electric vehicle, then I have to wait for at least 2 hours, 3 hours, sometimes 4 hours to completely charge the battery and then drive from there. So it has these current blocking points in terms of infrastructure. Yeah, that's why I cannot really answer how many or any charging station in India, but there are definitely charging stations in India. We need to search in Google.
Thank you, sir. Thank you. And one more question,
No
sir. What are the parameters to be monitored while we are connecting the charging stations, sir? Because electric vehicle has some parameters. So in perspective of a power system stability or voltage, so what are the parameters mainly to be monitored? Because this is a trending area in research for an electrical engineer. So what are the most parameters to be monitored?
Okay, I also didn't work in this battery technology, but what I know from overview is that if you go to a charging station, the charging station itself is providing an outlet which is having as much less fluctuations of AC power as possible. That is first step. And once you get this outlet available, you use a specific standard cable to charge the electric battery, because each manufacturer has certain standard connectors. So some of them have common cables, but some of them have specific cables as well. So you need to buy this electric charging cable. And this cable, if you just plug into the socket of electric charging station, and if you then plug the other end to the car internally has a charger, right? So AC to DC charger. This is where the complete algorithm goes in. And this is where the complete characteristics are being monitored. And there are not really many characteristics to look at the charging station itself, because charging station itself is just an AC power supply. So it has not too many parameters to look at. But what is on the other side is interesting to develop a charger. To develop a charger, it has to take in the AC inlet, which is coming from the supply, from the charging station. And this AC input has to be really properly converted to the DC, for which it has to check for the voltage and currents of each cell. So it might get the information from battery management system, or sometimes it might also have direct information from battery pack as well, from sensors. So they have to, of course, monitor the voltage current to measure parameters. And I don't know if there are any other sensors available in every car, like capacitance, resistance across the circuit, if it has to be measured. But each leg and also each cell battery voltage and current are really the important factors. It has to be checked and it has to be verified across limits. So we have to check for the minimum and maximum limits, and also to see how other cells are doing or other legs are doing, and also compare it continuously inside the algorithm. Yeah, as of now, what I know is the cell balancing equalization requires cell voltage, cell current, and leg voltage, leg current, such parameters. And across the complete circuit, we also measure the impedance, which also internally contains the resistance, capacitance, and so on. So these are the major parameters we look at.
Right. Thank you, sir. Any algorithm you followed, sir, for your testing in your Tesla? Any particular algorithm, actually?
Okay. I don't know. I have not worked for Tesla, but anyway, I'm also working mostly on the inverter controllers. So we have different controllers in the car. So we have battery, and battery requires a battery controller, which is called battery management system. So this battery management system itself looks at all these cell balancing, equalizing, and parameters as well. And I don't know which algorithms are exactly used inside the BMS. So you can always go to Google and search for BMS, battery management system algorithms. Maybe you can have some list. I have really not explored into this area. Sorry.
Yes. Thank you, sir.
Yeah.
Thank you. Thanks.
But I can provide some links later. Yeah. And as I'm working on inverter controllers, so in the inverter controllers, we have several algorithms. These I can give one or two examples later. But the similar way we can also have for the battery management systems. Yeah. Exactly. And I don't know what it does mean about 369. Yeah, I don't know if it has any code meaning. I also have to search on internet. There are many models in Tesla. Some of them they call it as 369 model, maybe some fancy number, or maybe it has some really reason. I really never explored into it. Yeah. Yeah, exactly. So I think we have seen all the questions, but we also have some minutes at the end to have some questions from you as well. Muthu sir, can I know until when we have the time to continue our session?
Our session 2 to 4, sir. Next 1 hour we have.
Okay, fine. So based on that, I will progress presentation.
Yes, sir. Yes.
Okay, then I'll continue further here. Let me close chat. Okay. So to continue, coming back to the battery pack, we have seen how the several cells are series parallel combination and how they have been used. And I think here it is. So not only the parameters, so like one of the colleagues have asked just now. So not only the parameters, there are derived parameters from the existing energy calculations, like from voltage, current, and impedance. We also can calculate over a period of time certain energy. And also there are internal formulas that can run to really see how the energy density is accumulated and how each cell is really being effectively used. So there are several possibilities. So I'm not saying that here, but for example, here they have battery energy density to compare between several types of batteries, lithium ion, nickel. cadmium, and so on. Yeah, and based on which they also have observed over a period of time how is the cell price. So battery cell price is also declining slowly because of the increase in technology, increasing cheaper overall manufacturing costs, but it is still the most expensive one. Yeah, similar to battery, which has voltage, current profiles observation. We also have for motor torque speed profiles, which is also very important to observe how are the torque speed characteristics working for a vehicle, for a motor. Yeah. Here we have some energy curves, which you can also see later. Performance versus efficiency, or the acceleration versus performance. Yeah. Okay. So what are the challenges in general? So long charging times, as we already just discussed, very short. So battery requires really long charging time compared to the refueling times. So that's one of the most problematic thing with respect to infrastructure. And battery weight is also very high and is also very expensive. So battery costs, and it doesn't have proper infrastructure with many charging stations or very frequent charging possibilities during the road journey, and that is also a concern right now. Yeah. So range concerns. So range concern is what we see, that if we use a battery of 400 volts and maybe 100 ampere hour, for example, and if it is giving a range of 200 kilometers, and people have to charge, let's say, for every 150, 200 kilometers to go further. If the journey is for 400, 500 kilometers, they cannot travel with one charge. So with one charge, they can only travel up to 200 kilometers, for example. That is called range. And this range has been improved in the recent years, especially from Tesla. It is a pioneer and making benchmarks in every aspect. And also in the range, it is trying to give up to 700, 800 kilometers. It is in plan, I think, which then is a really great advantage of using electric cars. With one charge, you can really drive that long. It's really advantageous. Yeah, but also it's expensive. So the range is directly proportional to battery, and the battery is directly proportional to the price. So some more expensive again. That's why price is what is one of the concerns, and consumer acceptance because of the infrastructure issues of charging, charging stations, and the pricing. The consumer is not able to accept to buy it in the immediate instance. But because of the regulations imposed by governments and subsidies given, and parallel and renewable energy sources which are in development process, it is trying to make consumers to accept more and more. And it happens also in the next coming years that people can use more hybrid and electric vehicles on the roads. And market is also based on consumer acceptance. If the consumers are coming forward to accept the hybrid electric vehicles, the market share also increase in that regard. Yeah, so general air conditioning, how it works, we may not discuss too much in detail, but it takes, so air conditioning requires compressor and motor, and these compressors also take energy from the battery powered motor output, and also it is trying to use the condenser fan, which is at the very front of the vehicle, so that if the vehicle is driving, it takes in the air available to cool the internal or cool or heat the internal elements. So air conditioning is done in that way. And some of the energy which is not sufficient from the radiator fan, it can also use it from battery. Yeah, so how is the energy efficiency at the moment if you just compare between electric cars and diesel cars? So they have given just in miles per gallon. So this electric energy is just converted into a diesel parameter so that the comparison could be easier here. So we already see there is a lot of difference. We also have a quick look at the efficiency of it later in our presentation. And yeah, running costs can be reduced if it is an electric car, and maintenance is reduced, and of course environment friendly where zero emissions. And if you really come across any electric vehicle which is driving beside you, you can almost hear no sound. It just starts off very smooth and low noise, that you can also see. And these are the advantages and future developments. So this is from 2011. So in the last 10 years, we have a lot of developments, but the development areas are still the same because they still have to be developed with advanced technologies, improved onto it so that the cost efficiency can be improved. So batteries are always in the first priority to improve its technology so that it can come for a cheaper price, it can come with a better pack of performance and energy density. And these are the challenges that is in the battery technology at the moment. And there are also parallel technologies emerging with the fuel cells with, I think, fuel cells is one of the alternatives to really use it instead of batteries, but still not the most stable ones. That's why it is not still in the market. Yeah, and solar panels are also okay, but not so effective because the output power is not really suitable for the passenger cars to drive to the satisfactory levels. Yeah, so these are some of the example models, how they look like from Chevrolet and Ford with the hybrid models. So these are some of the references, you can look into it later. Yeah. So we have seen what are electric hybrid vehicles, what are the major components, how they work, and what are their implications to some extent. So we have not gone very deep inside each of the elements, each of the algorithms, but we have seen on a basic level, overview level, what it contains and how they work. Now we go a little bit too deep into the technical diagram of it, but we also don't discuss that much time. Here we have the 4-quadrant operation. So if you take any motor, it can operate, any machine can operate in 4 quadrants. And if you link and relate that to the car, or can you please mute? Yeah. Okay. So here we have 4 quadrants, and we see here torque on the x-axis and speed on the y-axis. And of course, on the right side of axis is for the torque positive, and upper is positive for the speed, and downwards is negative. And the left side of the torque x-axis is negative. And M is for the torque representation, N is for the speed. And you can see here in the first quadrant, torque is positive, speed is positive. So the vehicle has to drive with the energy taken from battery. So this is a positive energy which is available from battery, and it has to be transferred to the motor so that it can drive the car. This is the first quadrant. The second quadrant, which is braking. So if you're braking in the forward motion, so the rotation is the same. It is driving the clockwise, but the energy is free. So there is no torque required from the motor, but it is actually available already at the output of the motor. So it is reverse. And when there is a counterclockwise torque available, and if you can always just say multiplication of torque and speed, real speed is the calculation of power, right? So here is power positive, here power negative, because both of them are having different signs, positive into negative. So if there is a negative power, which means the energy is available at the output, which is available on the wheels, this can be used to charge the batteries. And here again, having both anti-clockwise, that means it is on the reverse direction of the vehicle, let's say, and it also requires a torque to drive the vehicle. And this is anti-clockwise. So both are negative, negative multiplied with negative is a positive again. So it needs energy from the battery. So in the fourth quadrant, it is also braking, but the vehicle is still running backwards, but maybe downslope backwards, for example. And in this case, the torque is available positive and the speed is negative. So the combination multiplication of them is having negative energy, negative power, and this negative power can be used to charge the batteries. So during the braking phases here, quadrant 2 and quadrant 4, it is possible to charge the batteries and use the energy effectively. Yep.
Sir, negative energy means charging of the batteries.
Yeah, negative power. Yeah, charging of the batteries.
So the both the second and fourth quadrant is for charging and charging the batteries, while
Yeah,
the
charging and braking.
first and third quadrant becomes a discharging of the batteries.
Exactly.
Okay, sir. Okay, sir. So while at the time of braking our electric vehicle, but the power is to be come from the batteries.
Can you repeat
While we
the
are
question,
applying,
please?
while we are applying braking to our electric vehicle, where
Mhm.
the power come from the braking?
Yeah, so if you see, let's maybe go to paint. So let's say we have let's quickly say battery, and here is inverter, here is machine, and maybe here is the load or car, let's say load. So during normal process of driving the load or driving the car, the battery has to supply. This is quadrant 1 and quadrant 4. During braking, sorry, quadrant 3, I'm sorry. Yeah. Quadrant 2 and quadrant 4 is for braking. So which is in this direction. So during braking, that means you're trying to press the brake pedal, and depends on how much braking impact that car requires. So let's say if you press lightly, this is a light braking, and the machine deceleration, which means the energy is having on the load, and it is not driven by the energy available here, rather it has energy on the mechanical side here, and machine is already trying to rotate to reduce the energy here. So at this point, if there is energy and if you're trying to rotate some inertial machine, even if you take any, it is basically acting as a load or weight on this point. So if there is a weight on the shaft that is just rotating, it is trying to slow down the vehicle. So it is adding the weight, adding the reverse torque on it, so that it is trying to reduce. And if the brake pedal is pressed a little bit more, so if you need more up, let's say sudden braking, during sudden braking, you cannot rely on machine braking, because if the weight of the power, the against negative power that is trying to keep on the load is not enough. Then it is trying to use the brake pads, and these brake pads are trying to close onto the wheels, and then it stops. So the exception is if you want to have stronger braking and sudden braking or emergency braking, it cannot really effectively give regenerative. That means it cannot charge effectively batteries. But if you're just, let's say, slowing down, so you don't need high speed, you just remove the accelerator pedal. And if you're not pressing the brakes, it is trying to slow down, because the braking energy, the braking effect is already created by the machine, its weight, its load, and its reverse torque. And it is then also trying to use the available electrical energy here to charge the batteries. And if you're pressing a little bit slightly the brake, and it also can charge the batteries. So it depends on how strong your braking requires. It then combines between the actual machine and braking effect due to the regenerative braking, and also the actual brake pedals.
Okay,
Did it
sir.
answer
Okay, sir.
for the question? Yeah.
Yes, sir. Yes, sir. But at the same time, just I can't obtain. While for the second and fourth quadrant, the battery becomes charging. That's what I am not able to understand, sir. That is while we go for a braking, how can we say that is while applying a braking means the battery energy is to be as somewhat discharges only. How can we say that is a charging?
Okay. Okay, let's put it in this way. This is called discharging.
I'm not understanding this way. I'm asking, sir.
Yeah, no problem. This is called discharging process, right? From battery to load. Yeah, that is clear. It is
Okay,
discharging.
sure.
That means whenever you are trying to generate energy from battery and to drive load, it is discharging, always discharging.
Sure.
And during the braking process, you don't need any energy to break the load. Let's say you have reached 50 kilometers per hour and you don't want more acceleration and you just want to go with the flow. So you just remove your leg on the acceleration pedal in the car. You remove the acceleration pedal connect and it just drives to some distance, let's say with the 50 kilometers per hour on a specific road profile. If you're removing leg on your acceleration pedal and if you're not keeping any leg on brake, it can maybe, let's say, travel for 500 meters.
Sure.
Okay.
Sure.
During these 500 meters, you don't need any energy to supply to the car to drive for these 500 meters until it gets to stop.
Okay.
It is automatically rotating because of the initial inertia available at the point that you have removed the leg from acceleration pedal. And this is the free kinetic energy. So when the free kinetic energy is available, it is not taking any energy from any source. It is just freely rotating.
So at the time the battery functioning is?
Yeah, at the time, let's say if you, let's say theoretically, hypothetically, if you don't want to charge your batteries, where this energy goes, what is available. So if you are disconnecting the battery using a disconnector.
So just is idle condition.
Yeah, idle condition.
Okay,
the load has to dissipate all the energy available in rotating machine and the machine output goes to inverter, but inverter output is open circuit. So it cannot really add any load in the reverse direction. It is only having free wheel and it is trying to reduce the speed or reduce or getting the car into the halt position after certain time, after 500 meters of distance travel, only by dissipating the heat in terms of machine rotation and in terms of trickle energy dissipation in inverter and electronic components. So majorly, it is trying to waste as a heat by rotating the machine, friction and heat by rotating the machine. So in the ideal situation, the energy just being wasted and it is just being dissipated as a heat if you have disconnected the connection between battery and inverter. This is a hypothetical case 1. And in the case 2, which is the normal case which we use in most of the vehicles, is instead of wasting this energy, you just attach the switch here between battery and inverter. So battery is available here and energy is available here. So in the previous case, in the open circuit, it cannot transfer any current because it is open circuit. Now it is, since connected electrically, circuitry is closed, it is trying to send the energy from here to here by making the current to flow in this direction. Once the current is flowing in this direction, battery is not giving any power output, rather it is trying to charge the cells. So this means we are not using any energy from battery to brake the system. There is a natural braking available and this natural braking machine output, output is being used to just transfer to battery. We will also see a short video, maybe in the next 5 minutes, and that will also clear some of the doubts. So is it okay until here?
Okay, sir. Okay, sir. Fine, sir. Thank you, sir. Thank you. Thank you.
No problem. If it is still not clear, I think after the video, we will come to this point again.
Yeah. Definitely, sir. Definitely, sir. Okay, sir.
Yeah. So these are the basic directions of 4 quadrants and 4-quadrant operation of electric car.
Sir.
Yeah. Okay. Then we come to the same point which one of our colleagues have asked. This is an interesting concept and also sometimes difficult to understand. Let me check if the audio is available for you. Let me how to audio. let me know, sir, if the audio is available or if it is audible. Is it audible? No, right?
Not audible, sir.
Not audible.
Video came, but not audible.
Was it audible now?
Was it audible now? Was it audible now? Was it audible now?
Sorry.
Was it audible now? Was it audible now?
Hello.
Sir.
Was it audible before the audio?
Was it audible? It is not audible.
The audio from the video was not audible, is it?
Yes, sir.
Okay, I will try to play once again. Please let me know if it is audible. Just a
Yes,
minute.
yes.
Let me know if
Hybrid and electric vehicles can use an electric
Audible, sir.
Okay. Yeah, just let me. Okay, let me play it from the beginning. And also visible, right?
Yes, sir.
Okay. Yeah. So this is about regenerative braking. Just 2 minutes video, but it has really good information from Bosch.
Braking is the recovery of kinetic energy during braking. In a conventional vehicle, a majority of the kinetic energy is converted during friction braking into heat and emitted
Sir, some echo came, sir.
Seems some problems. Since I think I have connected in two systems, it is showing some trouble. Let me do one thing. Am I still audible, sir?
Not audible, sir.
Okay, am I audible, sir? My voice?
Yeah, your voice is audible, sir.
Okay.
Is it a website available, sir? In that link?
Yes, it's available.
Yeah, if possible, shall I open it and shall I run here and shall I share the screen?
Sure, sir. I can share the link right away.
Yeah.
That would be a good option.
Yeah.
Yeah, please share and play it, sir.
Is it okay, sir?
I couldn't
I'll
hear
run
anything,
this.
but yeah,
One
please
minute,
run.
1 minute.
Yeah.
Yeah.
Regenerative braking is the
battery
in a conventional vehicle, a majority into heat and emitted unused into the environment. Hybrid and electric vehicles can use the electric motor to recuperate at least a portion of the kinetic energy for reuse. The driver steps on the brake, the vehicle's electric motor switches to generator mode. The wheels transfer the kinetic energy via the drivetrain to the generator. Through its rotation, the generator converts a portion of the kinetic energy into electrical energy. This energy is stored in a high voltage battery. The generative braking torque of the electric motor, which is the result of energy generation, decelerates the vehicle. At low speeds, for example, shortly before the vehicle comes to a stop, the electric motor can no longer supply sufficient generative braking torque, and the friction brake must be activated. To maintain the required deceleration, the braking torque from the friction brake is continuously adapted to the current generative braking torque, a process called torque blending. In the case of full braking or an unstable driving condition, the vehicle is usually decelerated solely via the friction brake, as wheel-specific interventions are required. Regenerative braking enables an extended range in electric vehicles, as well as lowering fuel consumption and improving CO2 balance in hybrid vehicles. Invented for life.
Yeah, can you play it once again, sir?
Okay.
Regenerative braking is the recovery of kinetic energy during braking. In a conventional vehicle, a majority of the kinetic energy is converted during friction braking into heat and emitted unused into the environment. Hybrid and electric vehicles can use the electric motor to recuperate at least a portion of the kinetic energy for reuse. When the driver steps on the brake, the vehicle's electric motor switches to generator mode. Wheels transfer the kinetic energy via the drivetrain to the generator. Through its rotation, the generator converts a portion of the kinetic energy into electrical energy. This energy is voltage battery. Generative braking torque of the electric motor, which is the result of energy generation, speed. Shortly before the vehicle comes to a stop, the electric motor can no longer supply sufficient generative braking torque, and the friction brake must be activated.
compulsory, IST can be done next year.
Acceleration, the braking torque from the friction brake is continuously adapted to the current generative.
Last time Shruti ಎಷ್ಟು ಕೊಟ್ಟಾರ?
Braking or an unstable driving condition, the vehicle is usually decelerated solely via the friction brake, as wheel-specific interventions are required. Regenerative braking enables an extended range in electric vehicles, as well as lowering fuel consumption and improving CO2 balance in hybrid vehicles. Invented for life.
Okay.
Yeah, thank you, sir.
Yes, I stopped the sharing.
Yeah, I will share again. Yeah, there were some echoes and in between disturbances, so I asked for playing for the second time so that people can hear it clearly.
Yes, sir.
Yeah. It's actually interesting if you have really heard of the complete information that is kept in this video. There was one term which is used at the end, very, very important, torque blending. So this is the phenomenon and concept that is required in the EVs for the regenerative braking. So torque blending is a concept to share the reverse energy or the negative power available to distribute between brakes and what a motor can do. So the machine itself is acting as a brake during the braking process, and because of which it is trying to generate the electricity and trying to use this electricity to charge the batteries. So this is from the motor side. On the other side, if you're pressing brakes too hard, it also has to balance it to stop the vehicle as per the consumer or driver's expectations. So it also has to use some of the brakes energy to really go into friction and stop the vehicle. So based on how much power and how much force we give on the brake pedal, the torque has to blend between the actual available e-machine and the actual brake pedals. Yeah, this is there is of course this algorithm which is going to decide how much energy can be regenerated to charge the batteries, and how much energy it has to dissipate through brakes based on the braking demand from the driver. This is very, very important. And the colleague who has asked before about this regenerative process, is it clear now, sir, or still you have some doubts?
Sethuraman, sir?
Yes, sir. Yes, sir. So the battery is normally in terms of bidirectional way, is sir?
Yeah, exactly. So any battery you take, let's even if you take your phone battery, phone, yes, if you keep in charging, it charges.
Okay,
and once
sure,
you disconnect the charger, you use it for discharging.
Okay,
yeah.
Okay, sir.
Exactly.
So yeah, so inside the one topology, or what type of topology is normally used for either charging or discharging?
What do you mean by topology?
That means we have charging the batteries or discharging the batteries in some level to some level. We are using some power electronic circuit, power electronics converter circuit. Is there any standard topologies available for maximum, that is the fast charging is available there for a particular topology of the power converter?
Yeah. So the general topologies are AC to DC converters. So in AC to DC converters, we have standard way is to convert AC with a bridge rectifier to convert to DC, but there are several electronic elements adding to it. Sometimes they have RL filters, sometimes RC filters, some RLC filters. They have some additional protection equipment sometimes. So it depends how and how the supplier is manufacturing it and how the supplier is designing it. But there are no specific information of how and how they are using it internally or how they are developing. It is basically the AC to DC converters. So you can design it and use it how it is required in the system.
So based on the car manufacturers also, the topology of the converter or the battery inside the battery, what type of the topology used, that one is differ based on the car manufacturers also.
Yeah, so let's say the OEM, the original equipment manufacturer, says that I have a battery pack for a 400 volts capacity and let's say 100 ampere hour, and you design a charger for me to make it suitable for this. And this is coming as a requirement to the supplier, and supplier says, yes, I can do that. And what supplier does is internally to his own technology, and he has no dependency on what the customer or OEM says. So the supplier says, I want to design a AC to DC converter, which is maybe a buck. Sorry, it's just a rectified system. So if it is a 2-level or 3-level or with some additional filters or extra additional components, elements, electronic elements for protection, it all depends on the internal design of the supplier. So he can decide what kind of hardware he want to use, what kind of algorithm he want to use to effectively charging and safely charging the batteries from AC.
Okay.
Yeah.
So in
And
place of as a electric vehicle, we are not applying any braking means. It was continuously go for discharging the batteries as an autonomous vehicle. Okay, sir. It's an autonomous vehicle. Just we have to predict what are the various stations are to be there. So we fix that one. We are not applying any braking means. It means that the battery inside the electric cord is continuously discharging.
That's true to some extent. Let's say exception that you have a downslope. If you have a flat road, or if you want to have uphill, of course you also always have to give continuous energy supply to the motor and load. So the battery has to discharge. This is a scenario one. Scenario two, you still have no leg on the braking pads, but you have downslope. So if you want to have downslope and autonomous vehicle, as you said, so no control from man on the brake pads, but internally the autonomous vehicle also controls the brake pedal. So let's say if you want to drive the downslope only with 50 kilometers per hour, like before, it has to brake to reach this 50 kilometers per hour. Otherwise, in the downslope, the speed will increase, right? It can go to 60, 70 kilometers per hour. To control that, internally, the autonomous vehicle also has to control the brake systems. And once the brake system is activated, it then checks for the torque blending, whether it has to brake some of the energy using the motor or the complete energy using the brake pedals, or to share between them. Or and the other situation, you don't want to brake and you just want to increase the speed with the downslope. So you are traveling at 50 kilometers per hour, and if you're going downslope, and it might increase up to 80 kilometers per hour, and if you're still okay with that, you don't use any braking on it. Rather, you also don't use any energy from the battery. Yeah, because it just goes with the gravitational force. Yeah,
gravitational force. Okay, fine,
yeah.
Sir. Fine,
So based on the desired speed, desired torque demands, it always regulates between the actual regenerative braking charge discharge cycles.
Okay. Thank you very much, sir. So at the same time, actually, I am in teaching field. I just suggested my students to develop one type of converter which is to be used for a bidirectional converter for charging the batteries in terms of fast manner. That is, the time is to be somewhat reduced. I just checked with the some hardware in terms of how much time is required to charge the capacity of the batteries in that one. But how can we implement our approach to the manufacturers or some that is in the market? How can you approach that in the market, sir? Because I developed one topology which is to be designed particularly for fast charging. So how can I approach to inform my innovation to the some car companies, some the manufacturers?
Yeah, I'm not sure how this works from the private parties. So normally what OEMs does is they go to suppliers directly. So they give the requirements list to, let's say, 10 suppliers. Suppliers, I mean, let's say Bosch, ZF, Continental, Magna. So they give to different suppliers. And each supplier then takes the requirements and see if the technology is already available to some extent internally, or if they have to build it completely new, and based on which they plan the complete project for certain time. And they give, they plan resources, they plan the internal technical team members, and also see how the concept is to be built, and that they prepare the timelines. If the manufacturer wants within 1 year, then they have to increase the resources in the team to make it faster with the technology. And internally, each supplier has a possibility, if the suppliers are already linked to certain universities, like yours, for example, they can then ask the internal universities to have internships or projects working with them. And if you already have a concept, and if you want to approach with this concept to the supplier, it is possible. So if you have contacts with the suppliers, if you have agreements with the suppliers that they give you your students and you the internships or working together with universities, then you can always propose to suppliers, and together with supplier, you can go to the OEM. Like you can propose a concept and it can be, if it is effective. There are like several concepts and it has to comply with a lot of things. So the problem here is the concept can be developed, but it has to comply with certain regulations with the automotive. So the automotive regulations states certain standards. So it has to meet certain safety requirements. It has to meet certain operational requirements. It has to meet certain market requirements. And it has to meet sometimes some country level internal requirements. So there are several requirements. It has to be divided and the complete concept has to be integrated to comply with all these compliances. That is the biggest problem here. Because even if you take the best concept towards to the manufacturer, he might agree that the concept is good, but then he can say, I don't really achieve the safety standards I wanted. So we need to re-implement or redevelop that. So we need to, if it is a private thing, I don't know how this can be approached, but you always can check in internet or in certain standard websites how the acceptance is done sorry, from the manufacturer for this particular product. And these acceptance requirements you can verify on your system. So the acceptance with respect to hardware, internal algorithm, and safety features. So the safety features, if you go, it's again an extensive topic. So there is safety for each level. So right from the electronic component of resistor, inductor, capacitor that we use, there is for every small component that we use in the hardware circuitry and every algorithm that we implement in the software, it needs certain standards to be met. So if you really want to go with that, you have to verify what are the standards and whether your product is meeting that. And if it is not meeting or if there are any deficiencies, you have to again implement it and develop it to prepare as a complete product. And then maybe there are sometimes open source informations available from the suppliers or manufacturers. You can go to each manufacturer's website and see what are their futuristic plans. If you see that there are some plans for taking in the charges or fast charging concepts, you can always send them an email that you have a concept and you want to discuss with them, and it is possible, I think, to discuss with them if they accept it. Yeah. So these are the several possibilities that you can have. Yeah.
Sure. Thank you very much, sir. Thank you, sir. Thank you for your valuable suggestions given for me, sir.
No
okay,
problem.
thank you, sir. Thank you. Sir.
Yeah. So no problem. So we will go ahead next to the next step of. So until here, it is about the information of electric vehicles. I have not touched the internal concepts of inverter control. And this is really one of the interesting topics as well. But I think for this session, it's really time-taking thing. And I also wanted to cover only basic concepts, not too deep into each of them. That's why I couldn't include it. But you can always look for what are the algorithms and concepts used for inverter control. So IDIQ control or DQ, Clark-Park transformations, how they use it, and space vector modulations. So I don't know if this is relevant to every person here, but these are the terminology you can always look for in internet and see what are the control aspects, or if possible, maybe we can see in any other future sessions into this topic. So this is these are the some of the technical aspects and historical aspects of electric vehicles till now we discussed, and we go a little bit to touch the engineering processes and the actual industrial touch of software and hardware development to the electric vehicles. So we have several models available inside each company. So theoretically, each company can follow different process. So why process is important? If there is no engineering process available in the industry, there is no tracking of the information, or there is no tracking of the development itself. Let's say the general process, how it works, even in the outside market, if you have a product, you approach several manufacturers or several OEMs in the case of electric vehicles. So original equipment manufacturers, you go to them and propose, okay, I have a concept here. If you have a requirement, please ask me. Or on the other side, if OEM has a requirement, he calls upon many suppliers and make a meeting and try to explain that what their requirements are, what they need. Then each supplier thinks about it. And each supplier is also given some time to think about it and to come up with the concept, to come up with the pricing, to come up with the offers. And then they agree together to which supplier they have to give which product. Let's say the OEM Mercedes-Benz. So the Mercedes-Benz as an OEM has requirement for several controllers like inverter controller, DC-DC controller, battery management controller, and airbag controller, and so on and so on. There are many controllers. And we can take one example of inverter controller. So for example, for inverter controller, he provides bidding for all the suppliers that, yes, I have a new model of car available, which might come in the next 4 or 5 years. And this new model has the requirements of this much power, this much range, this much torque speed characteristics, and they give all the features required for this car. And they call upon suppliers and they explain the requirements, and all the suppliers take up the requirements and they go back to their companies and they have a high level management meeting and high level technical meeting and divide those requirements into sub requirements and see what is possible. So maybe they were given like 2-3 months or 4 months of time to provide some sample. So this is just a sample development phase where they try to develop initial sample of hardware and software based on the initial concept. And then with the sample, they can estimate how much cost it could also be per unit. So if the OEM like Mercedes-Benz asks like, I want 10,000 units for this type of car model in the next 4 or 5 years. Then for this 10,000 units, if they want to manufacture, if the supplier want to manufacture and develop, how much per unit cost also will be calculated. Then for the next meeting after 4 or 5 months, all the suppliers again meet with the OEM, and the OEM have individual evaluation of each concept in terms of technical sophistication and also in terms of costs. If they both balance, that they cannot go for a very cheaper one if the technology is not so good and if it has some flaws. At the same time, they cannot go to the most expensive, most qualitative one because if it doesn't have too much difference with respect to some moderate costing equipment or moderate costing unit. So they then think what is really suitable for them, and they can give one particular supplier a bidding possibility or offer to manufacture. So once this is agreed between the OEM and supplier, and the supplier goes for the next 3-4 years with the development and also testing and release the product and manufacture the product and release the product to OEMs. So this is a very big process, right from requirements from OEM to development to test and release. And this is for just one model, one equipment, one particular type of device. And if you really think about companies, how they are operating, they have many electric vehicle models available from different OEMs, not only Mercedes-Benz, they can have from BMW, Volkswagen, Mahindra, Ford. There are many companies and many models available. And for each model, one type of particular development has to go on. And if a company has to develop so many such units with the different characteristics and different requirements, they need to follow certain process. And if this process is not followed, at the end, they don't know where to develop, how to develop. And if they have to look back after 10 years, if there are any bugs, errors, and failures happening, if they want to correct them, they need proper process to store every information that is happening through the development. And these are indulged into specific models. So any company can follow any model. And here is an example of V model. What is V model? V model looks like V, as you see here, right from left to right. On the left side is a project definition, which is like concept of preparations and requirements and architecture. So requirements are diagnosed into different small requirements again, and the architecture is made to see how the hardware software has to be developed, and the detailed design has to be made. And once the design is implemented, so this is the implementation phase, it has to go through testing phases, so several testing phases. They can test on an overview level, which is an integration test. They can do the complete test on a system level, which is a system level, and they do the complete operation maintenance test, maybe directly on the car. And each testing result has an implication on its on the left side requirement. So the operation maintenance tests are really verifying what are really in the concept done, whether it is really matching with the testing, the results are matching or not, they can do it. And at the system level, they match with the requirements and they match to the architecture, whether the architecture and requirements that are done in the beginning are really working right or not. And the integration test and verification, they do testing on a very low level where they have internal design of each specific thing, like hardware. They have a small circuitry for safety, small circuitry for IGBT, small circuitry for filtering. So each separate thing has to be tested, which is a separate test. And also it has to test together with software algorithm, which is also a small low-level test. And this has to be done for each concept. So if there is a regenerative braking principle, how it is working, if there is a DQ control, how it is working, if there are sensors for current, voltage and speed, and how they are working. So there are many internal tests that can be done. And this has to be mapped between several requirements. So on the left side is the project definition requirements, and the right side is testing of the requirement after the implementation is done. And with this, they have several tools in the background implemented to suit this model. And these tools are storing the data of requirements, coding, the implementation designs, and also the testing results and so on. And after 10 years, they can still come back and say, okay, my particular model release has used these requirements and it has produced these tests. And there is some error reported or failure reported from the consumer, and this has to be verified, which means they then take out the code that is latest available at that time, and then they can again modify it if needed to correct the failure and release a new version. So that's the reason, and as one example to exemplify how this is being used. So this is an engineering process, yeah, to simply put in. And I think we have reached the end of the presentation, so that's why I don't go too much deep into other aspects. Maybe we can see in some other future possible session if it is possible. So I just give 1 more minute to see the other documents here, how we can verify later. So the example of testings I have given here: Hill hardware in loop testing, SIL software in loop testing, Mill is model in loop testing, and high voltage test bench link is yeah. So this is also link available here. Just a minute. Yeah. So this link, you can have some testings available on test automation. Test automation is a use of special software and control execution of several steps of tests automatically. So we just start the test once and it runs for sometimes 2 days, 1 week, 60 days, and even 3 months and so on continuously, and gives the results at the end. And there is also a link provided here with the e-mobility concepts from ZF, where you can see also more detailed information of different types of electric drive configurations, motor used, inverters used, and what are the specifications. This is an open source document, so that's why I have given a link. It would be really interesting. Please go through it later. So with this, I would like to just say, I want to end the presentation and give 5 more minutes of my time here. I can stay here for 5 minutes if you have questions. And if you also have questions later, you can always contact on my Gmail or WhatsApp. I'm also giving it here in the document. I will share this document with Muthu sir later, and he can share with you as well. So if there are any questions, I'm here, sir.
Sir, is there any software is available for testing the batteries?
Can you repeat the question?
Is there any software is available for testing the batteries?
There are several softwares available. The problem is, are you planning to test in a real-time environment, or you want to simulate it?
In a real time, sir.
Real time. There are several tools, but I think I can only give you the company names, and we have to internally explore if they have such systems available. Like, I don't know, maybe just battery testing tools. Lithium battery testing equipment, for example. Yeah, for example, Binder is yeah, exactly. So for example, this is a temperature chamber and electric testing equipment. So Binder is a company which can be used. We have to see at what are different equipments available and their ratings if they are suitable for our current manufacturing product. So we have to explore that, sir. We need to see what is the range and rating of your battery pack, and what is the range that it can be used for testing. We need to just check with each supplier of several products and discuss with them and provide a solution to get the solution. And you can always Google it and see several list of manufacturers, a list of suppliers for that, and available in the market. So, for example, Rode and Schwarz, yeah, electronic testing tools. Yeah, don't know if they have. Is it okay, sir? So you have to search in the internet. I don't have any.
Okay, thank you, sir. Thank you, sir. Thank you.
I have
Very
a
fine.
list of suppliers like DSpace, ETAS,
Yes.
other, but they supply only for industries, and they might cost you more as well. So you may have to check in the internet and see and discuss with them basically your requirement and see if it is matching.
Okay, sure, sir. Sure.
Yeah.
Okay.
So any other questions?
Participants, any other questions? Yes, sir. It's a very great session. I think so. Any other questions? The last chance, people.
Sure, sir. One question finally. Sir, how much time it takes for implementing your product, sir?
Normal project time is, let's say, it depends on the complexity, right? So 4 or 5 years. Normally the project time is, it can vary from actually 1 year to 5 years. Let's say if it is a small technology for mild hybrid, it can be implemented quick, can be tested quick, and also released quick. So within 1.5 years, it can be done, the complete production. It also sometimes gets delays because of hardware equipment availability, production plants, operation availability, and so on. But 1.5 year. The bigger projects like plug-in hybrid or electric vehicle component implementation and algorithm implementations would take at least 4 to 5 years for each model. It can maybe be reduced in the future because in the next 4 or 5 years we have the technology available. If there is only slight change from the existing technology, then it can be done within 1.5 to 2 years as well.
Okay. What are the major difficulties you faced recently, sir?
Yeah, production. For example, because of COVID, there are a lot of plants. They are trying to avoid the personnel available there. So if one person in the manufacturing team got COVID, they have to be in quarantine isolation. So people, if they are not available in the production area, then it cannot be produced. So because of which there are several small parts which has been delayed from the production, and which also at the end gives a delay for complete system delivery. That is one thing. And other complications are related to technology. So there are many small companies that are also coming up at the moment, and they are operating on a competitive level to provide solutions to manufacturers for lesser prices and also with more features. And so we need to make sophisticated process or efficient process to be in the market and also to implement them at the faster pace. Yeah.
Okay.
So
thank you, sir. Thank you very much. Sir.
Yeah, no problem.
Thank you, sir.
Sir, shall we conclude? Shall I conclude?
Yeah, sure, sir.
Yeah, very thank you, sir. There is a very nice presentations today. So many people, they have cleared a lot of doubts regarding that electric vehicle area. So definitely these things are their takeaway for their research further. Then there is, I would like to introduce myself as well as my team. So can you please 1 minute to share our screen, sir?
Yeah, sure, sir. Definitely.
Yes, sir. Yes. So this is my team. Yeah, is it audible, sir? Is it visible?
Yeah, this is visible, sir.
This is our team. Along with that, another two people, Badunayak is here, and another two people, Hemant Sai as well as Narasimha Prasad. These people also done well, and their last year as well as this year. This is an entire team last year as well as continuing this year, as well as the remaining year also. We will continue with that. This is the small team for engaging with our work. And personally, my side, some people are asked about myself. Myself, 99 completed, 2005 MB completed, and 2017 PhD completed. My specialization power electronics, FPGA as well as MATLAB. So I have given nearly 30 guest lecture as well as so personally one journal also it is going on under my name. So I'm the editor in chief. Okay. Further, anything else you can contact me in these areas also. That is my email ID, my phone number and everything I have given. Yeah, and further that our college more than 20 years that is running. So that's all from my side. And participants, can you please open your camera for your the valuable photos, and these things are required. Participants, can you please open your photos for camera? Can you open? Yeah, I would like to change the view. Yeah, view.
Sir, I couldn't open my camera.
Yeah, is it okay? No problem. Those who are having, kindly share your camera. It will be more helpful for our many work. So,
sir, it says if the host has started.
Yes, sir. 2 to 3 photos. Great for us.
Problem, sir.
Then one more thing, totally around 150 people are average. At an average, 150 people are participated for various sessions. So 10 speakers are given their lecture grade well. So now is it great for, then once again, the important thing is I would like to thanks to the participants. So each and every participant, it's a valued for us. It's a great, thank you for your valuable suggestions also. And thank you for my team people, everybody worked well. Thank you so much. And the last thanks to my last speaker, Naharjuna Reddy Garu. Thank you so much for your very valuable session, sir. Thank you,
welcome, sir. And I'm also greatly privileged by having this opportunity to speak with you and speak with many of the experts here. Yeah, it was a great privilege, and thanks for inviting as well. Yeah.
Yes, sir. Thank you, sir. Thank you so much. We can wind up now. Now I will share. Sir, you can. Thank you, sir. I will call you, sir, now after 5 minutes.
Okay, sir. Thank you very much. Thank you all. Have a nice day. Bye-bye.
Yeah, participants. Sorry. Yeah, participants. Now you can fill the form for today last session. And the overall session I would like to give in the WhatsApp. Okay, so I'll share in both the side. In the overall session, we are asking your name and email ID and your name, your college name and everything. Kindly do it properly, because in the overall feedback form, which will display for your certificates. Okay, that is the in the WhatsApp, there is overall feedback link given. In the Zoom link, that is a session link I have given. Kindly fill the both the things, so which will be helpful. So due to data exhausted. No issues for that, for the last session feedback also, but the overall feedback is very important. Overall feedback is very important. Kindly fill the overall feedback. The day, your name and the college name and the designation not asked, but the department asked. And
overall feedback link is not opening, sir.
Overall feedback.
It is not opening. It is not working. Overall feedback link, sir.
Sir, overall feedback form is not openable.
We will send once again in the feedback link in the WhatsApp group, ma'am. Just please check once.
Sir, overall feedback is not working, sir.
Yeah, participants, now you can check. This is the link for overall FDP.